Okay, now if we want to use the periodic table to determine the configuration of electrons in a given atom, let's first remember that these two columns, the alkali and alkaline metals, represent the S block, and that these 6 columns, families ranging right over from main group 3 to the noble gases, represents the P block. The transition metals between groups 2 and 13 represent the D block, and of course these rare earth metals down here represent the F block. Now, we also know this is period 1, period 2, period 3, period 4, period 5, period 6, and period 7. Now, let's not forget that in this game of let's write the configuration, we do not think of these numbers as atomic numbers, the number of protons in the atom. Instead, let's think of them as each electron, from electron 1 up to electron 114. Depending on the atom, we could have that many electrons. And so we're going to read right off the table where each electron should be placed. And let's start with a simple atom such as sulfur. Well, sulfur has 16 electrons, as I can clearly see. And in order to place these electrons, I know that electrons 1 and 2, because I can think of helium as being right here, would go into an S sublevel, and it's the S sublevel in the first period. So I would write 1s with a 2. The 2 superscript, never a subscript, superscript, represents how many electrons are in the 1s sublevel. And yes, electrons 1 and 2 would go into the 1s sublevel. After 2 comes 3, and 3 and 4 are also part of the S block. It's just they're going into the second S sublevel. So that would be a higher principal energy level spherical orbital, 2s, and they're going to be 2 electrons. 4 down, 12 to go to get a total of 16. Well, if I can count, I know where the next ones go, because 5, 6, 7, 8, and 9, and 10, that's 6 electrons, all go into a P sublevel. However, there is no 1P sublevel. Don't forget from preceding information that the first time the second sublevel appears, you have to be in the second energy level. And this 2P sublevel would have 6 electrons in it. And that accounts for 10 of sulfur's 16 electrons. Then, of course, after 10 comes 11. And once again, I find myself in the S block. And 2 electrons can go into the next S sublevel. And of course, since every principal energy level has an S, the next one is the 3s. And I can put 2 more electrons into the 3s. Then, of course, after 12 comes 13. So electrons 13, 14, 15, and the last one, 16. These 4 electrons go into the next P. If this is 2P, then this has to be 3P. So I'd write 3P4 for 4 electrons. And yes, 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 4 is 16. I have accounted for all 16 electrons. Now there's another way I could represent this configuration using what's called the core abbreviated method. And it does shorten up electron configuration, so we don't have to write as much. And the way we use the core abbreviated method is, first of all, we determine the atomic number of the element we're interested in, 16 for sulfur. And then you select the next lowest atomic number noble gas. Now, if I go looking at the noble gases for something with a number lower than 16, the next lowest would be 10, neon's atomic number. And I can shorten up this whole configuration by using square brackets and writing neon in the square brackets. Now, what this means is up to this point, the first 10 electrons in sulfur all get arranged and configured just like neon would. And of course, that's 1s, 2s2, 2p6. In other words, the square brackets with neon inside is saying this to a chemist. And so now all I have to do is pick up with any electrons that are more than 10. So yes, 11 and 12 would still be 3s2, and these last 4 electrons would still be 3p4. And so this is the core abbreviated electron configuration of sulfur. And it is shorter, and you may be saying not much shorter, but if we were to use a very large element, for instance, if we were writing polonium's electron configuration, well, we'd have to configure 84 different electrons. But by using the core abbreviated method, we could start with xenon's core and then only worry about the remaining 30 electrons, because xenon's core has 54. And trust me, that would be saving considerable time. So things get a little more problematic when Ds are included, because when folks start counting electrons number 21, 22, 23, and so forth in the first transition metal series, and we're using D sublevels, they tend to look over here at the period number for which Ds these are, and that's incorrect. This is actually representing electrons that go into the 3D sublevel. And the way you have to remember that is, don't forget how many of these 4 sublevels you can have depends on which energy level you're talking about. If you're in the first level, you can only have 1 sublevel, S. If you're in the second principal energy level, you can have 2 sublevels, S and P. So it's when you hit the third sublevel that you can have 3 sublevels, S, P, D, and F. And yes, while this first group of D electrons is not in the third period, it is nevertheless the 3D electrons, which is telling you something. If these are 4s electrons, and we fill the 4s before we place the electrons into the 3D, it's telling us that 3D electrons actually have greater energy than 4s electrons, because this writing of configurations, as we said last time, follows Aufbau principle, German word for building up or building outward. And so we are placing electrons from lowest to highest energy sublevels. And if we fill the 3D sublevel after filling the 4s, the periodic table is trying to tell me that 3D electrons are more energetic than 4s electrons. So in any event, let's choose an atom. Let's just say cobalt. It has 27 electrons that we wish to configure. Well, 1 and 2, so the first 2 electrons of any atom would go into the 1s sublevel, so 1s2. 2 is followed by 3 and 4, which are 2s sublevel electrons. 4 is followed by 5 through 10, and this is the 2p, the first p sublevel, and that's 2p, not 1p. 1p doesn't exist. 2p sublevel with 6 electrons. 10 is followed by 11, and once again we find ourselves in the third s sublevel, so 3s2. 3s2 is followed by 13 through 18, which is, if this is 2p, this is 3p. Got to keep track of which p you're talking about. 3p6. After 18 comes 19 and 20, and this of course is the fourth s. We never have to worry about s's because they line right up with the period number. So 4s2. 4s2, then we go from 20 to 21, and all of a sudden we find ourselves in a D sublevel. And we have to remember that n must equal 3 to have a third sublevel. So this is not 4D. I know it's in period 4, but it's 3D. It's the first D. And we write 3D with 1, 2, 3, 4, 5, 6, 7 electrons, 3D7. Now, of course, we could use simpler notation, the core abbreviated method, to represent this as much shorter. And the way we play is we say, well, cobalt's atomic number 27, and the noble gas with the next lowest number is argon, 18. So I can save a lot of time by saying in square brackets the configuration of cobalt is the same as that of argon for the first 18 electrons. And then I just pick up with the 19th through 27 electrons. And 19 and 20 still are in 4s. And then the last 7 are still in the 3d. So yes, I have greatly truncated by using the core abbreviated method with the atom cobalt. Now, as our next example, let's pick a really complex atom. Let's go down to something that actually is down here in the rare earth metals. Let me select my pen, and let's go down to, say, this atom right here, atomic number 61. We play the same game, except we're going to have to count upward from 1 to 61. 1 and 2 are still 1s. 3 and 4 are still 2s. 5 through 10 are in 2p. The first p is 2p. And then 11 and 12 are 3s electrons, 2 of them. And then 13 through 18 are, if this is 2p, I remember that's 3p, 6. After 3p comes 4s with 2 electrons. After 4s, this is where we hit the d's, and the first d is 3d. And with the 5d orbitals, you can accommodate 10 electrons. No need in counting, there are 10. Then 31 through 36 are in a p, and if this is 2p, 3p, this must be 4p, 4p6. Takes us up to number 36. 37 and 38 are 5s electrons. 38 is followed by 39 up through 48, and that is 10 electrons, and if this is 3d, this is 4d with 10 electrons. Getting closer, because I'm up to 48 electrons and I need 61. Well, afterwards we get 6 more p's. This is 2p, 3p, 4p, this is 5p. 5p6. Running out of space, I'm going to continue down here. And after 5p6, we get 55 and 56 in the 6s, 2 of them. Now after 56 comes 57, and that's not here in the d's, that's down here in the first series of f orbital electrons. And let's not forget that f's do not appear until the 4th energy level, n equals 4. And that's because we have 1, 2, 3, all 4 sublevels if we talk F, and you must have at least an energy level equal to the number of your sublevels. So the first time we can have all 4 sublevels is when n equals 4. So these F's are 4F electrons. 1, 2, 3, 4, 5 of them. And there is our electron configuration for the atom. Of course, we can greatly simplify this, because if I use atomic number 61, the next lowest core noble gas in atomic number is xenon. So I could write xenon in square brackets and account for 54 of the 61 electrons. It's all of these accounted for by simply writing xenon core. Much simpler. But then after 54, I pick up with 55 and 56, which are 6s electrons, and I round it all out with the last 5 electrons that are in the 4f. So what you can see here is complete electron configurations can take an awful lot of time, but if we use the simpler core abbreviated method, it can take us a lot less time to write these configurations.